the exercises of Chapter 3, the bonding theories. In this exercises, I will follow several methods to solve the exercise. At the beginning, I will use the classical method, for example, to find the geometry or to write Lewis structure. And in other exercises, I will prove a method to find directly Lewis structure or the geometry without drawing. So now in the first three exercises, I will follow the classical method to solve the exercise. Which of the following species has a triple bond CO2, C2H4, NH3, C2 minus H2CO. So now we have to find what is the strategy to solve this exercise. To know if a molecule contains a triple bond, the easiest way is to write Lewis structure. I can eliminate the NH3 molecule since it's impossible to have a triple bond between N and H. The hydrogen follow the do-it rule. So the answer is between A, B, D, and E. In these molecules, we will count the total valence electrons. In CO2, we have 4 for carbon plus 2 times 6, 16. In C2H4, 2 times 4 plus 4 times 1 equal 12. In C2 minus, 2 times 4 plus 2 minus. Pay attention, when you have an ion, you add the electrons, and when you have cation, you remove electrons. So this is an ion, we have to add 2 electrons, so 10 electrons. H2CO, 2 times 1 plus 4 valence for carbon plus 6 for oxygen, we have 12. In CO2, the central is carbon. In C2H4, we have 2 carbon centers. In C2, 2 minus, we don't have centers since this is a diatomic species. And in H2CO, the central is C. So we draw Lewis. In CO2, we have to join the carbon to 2 oxygen. Then we distribute. We distribute 6 lone pair on the oxygen. We have to add 1 lone pair and 6 lone pair on the second. And we will find that the carbon does not have orbital completely filled. So what we do, we transform a lone pair from oxygen and another lone pair from oxygen, or we transform 2 lone pairs from the first oxygen. So we obtain the structure. Okay, this is CO2, which is the best. So we have 2 possible structures: O, triple bond C, single bond O, or O, double bond C, C double bond O. We have to choose the best by using the formal charges. This is the best. For C2H4, we obtain the structure. For C2, 2 minus, we have total 10 electrons, so we join 2 carbons by 2 electrons. Then 10 minus 2, we have 8. The 8 are distributed on the outer atoms, so we distribute 6, and we have 2 electrons remained. So 2, 4, 6, 8, 10. And the brackets 2 minus, this is a notation, and pay attention that 2 minus are counted before. 2 minus, this is notation to make the difference between the Lewis structure of C2 2 minus and C2. The second carbon has total 4 electrons, so we need 4 more electrons. We transform 2 lone pairs, so we obtain this structure. For HCO, H, the first distribution will give structure 1, and we need to transform 1 lone pair from oxygen, so we obtain HCOH. According to these structures, the molecule where we have triple bond is in C2 2 minus species, so the correct answer is D. Exercise 2. Which of the following does not conform to the Lewis octet rule? I advise in this exercise to put directly the answer, since we know that for boron, for aluminum, for example, and for hydrogen, we have exceptions. So we can write directly the answer is D. It's not necessary in this type of exercise to prove that BF3 does not follow the octet rule, but I will solve. So boron is known as an exception of the octet rule. The boron has electronic configuration 1s2, 2s2, 2p1. So the boron has 3 valence electrons, 3 plus 3 times 7, so we have 24 electrons. Okay, so the structure is the following. As I said, we could not transform a lone pair from F to boron in order to have the octet rule, so boron is an exception, and I will explain in the next chapter why F could not transform a lone pair to bonding pair. So the correct answer is D. Exercise 3. Consider the following species which contain odd number of electrons. So in this type of exercise, we have to count directly the total valence electrons in the species. In BrO3, the boron has 7 valence plus 3 times 6 for oxygen, so we have 25. HO2 minus 1 plus 2 times 6 for oxygen, and we add 1 minus, so we obtain 14 electron. For N2O, 2 times 5 plus 6 equals 16 electron. SO3, the total valence electron of sulfur is 6 plus 3 times 6 for oxygens, so we obtain 24. In SO3 minus, it's not necessary to recount the total valence. The SO3 minus is obtained from SO3 by adding 2 electrons. So if we have 24, we will have in SO3 2 minus 26. So the correct answer is only the structure of BrO3. So the answer is D. Which of the following species in the following list is square planar BF4 minus and BF4 minus, SF4, xenon F4, Si4, or PCl4 minus. All the species, the central atom is tetra-coordinate. So we have possibility of 1, 2, 3, 4, and 5 to be square planar. In other words, we could not find directly the answer. So for a square planar geometry, the simple form AXM-EN should be AX4-E2. In all examples, the F, the X is F. The central atom A has 4 outer atoms. So around the central atom, we have 4 bonding pairs, and we have 2 lone pairs or 2 non-bonding pairs. I try to analyze the structure of the square planar geometry, because in the next exercise I will prove a rule that can be used directly without doing all this work. So the central atom has 4 bonding pair and 2 lone pair. A share 4 electrons of its valence. Why? Because A did 4 bonds. And A has 2 lone pair. So around A, I have 4 electrons shared, and I have 2 lone pairs. So around A, the total valence is 8. So A should have initially 8 valence electrons. That means 8 is in group A is in group 8. A is in group 8. So in this list, in the structure xenon F4, I have a xenon, which is a rare gas. So the correct answer is for the structure xenon F4. So the correct answer is D. In this exercise, I did not draw all structures. I find the real or the correct answer by analyzing the structure square planar. What is the meaning of square planar geometry? So the correct answer is D. Can we use or can we solve this exercise by another strategy? Yes, is to write Lewis structure for H, then find AXMEN. In BF4 minus, you will find AX4, so the geometry is tetrahedral. In SF4, you will find AX4E, so the geometry is seesaw. In xenon F4, you will find AX4E2, so the geometry is a square planar. In SIF4, the simple form is AX4, the geometry is tetrahedral. And in PCl4 minus, you will find AX4E, so the geometry is seesaw. But this method of solution takes time, so it's better to use the first strategy. Exercise 5. Which of the following species is trigonal planar? ClF3, BF3, ClO3 minus, GeCl3 plus, SiH4. Trigonal planar, that means the central atom did 3 bonds. So all answers 1, 2, 3, 4, and 5 are acceptable for this question. Now, I have to prove, or I will prove a method, and this is my own method that can be used directly in the exercise. Is it necessary to write the Lewis structures for all molecules or species, then deduce AXMEN, then deduce the geometry? No, it's not needed, because we will study the general proof. All have 3 outer atoms, so possibility of trigonal planar shape. The trigonal planar shape is AX3 E0. This is the simple form. I will prove a formula. What is the non-bonding? What is the number of non-bonding electrons? In a structure AXMEN, I have X bond. I have M bonds. Since I have outer atoms equal to M. So A is bound to X, this is 2 electrons. A bound to another X, another 2 electrons. To the third X, another 2 electrons. So A is bound to MX, so I have 2 M bonding electrons. I have 2 M bonding electrons. So the total valence electrons are distributed, a part for the bonding and another part for the non-bonding. So the non-bonding electrons is equal to the total electrons minus the electron bonding minus the electron distributed on the outer. So if A did a bond with X, around X I will have 2 electrons. Then I have to distribute around X 6 other electrons in order to have the octet rule. So the non-bonding electrons is equal to the total electrons, the non-bonding electrons, I mean E is equal to the total electrons minus the electrons involved in the bonding of the central outer minus the electrons distributed on the outer to have the octet. So I distribute on each outer 6 electrons, and how many outer do we have? I have M. So the non-bonding electrons is equal to the total electrons minus 8M, minus 2M, minus 6M, so it's minus 8M. Now count by using this rule, and this rule, in my opinion, is not found in the books. Okay, this is a simple rule to find directly the non-bonding electrons. Count the valence electrons by using this rule. For ClF3, I have total valence electrons 7 plus 3 times 7 equal 28. Find En. How many electrons do we have in total? 28. So 28 minus 8 and M equals 3. So we have 28 minus 8 times 3. So we have 28 minus 24. So the form is AXM En equal AX2E2. Pass to BF3. We have 3 for boron plus 3 times 7, 21. So we have in total 24. Apply this rule. What is N? The non-bonding electrons or the non-bonding pair. So we have 24 minus 8 times 3. So 24 minus 24, this is AX3E0. For ClO3 minus, we have 7 plus 3 times 6 plus 1, so we have 26. Apply this rule. We have 26 minus 8 times 3, so 26 minus 24, so we have E1. We have 2 electrons, that means 1 pair. GeCl3 plus, is that the total 4 plus 3 times 7. Pay attention, we have a plus, this is cation, so we have to remove 1 electron, we have 24. Apply this rule, 24 minus 8 times 3, so 24 minus 24, and the formula is AX3E0. Si, H3 minus Si, the total valence equal 4 plus 3 times 1, and we have 1 minus, it's anionic, so we obtain in total 8. Find now N, 8 minus 3 times minus 3 times 8 minus 3 times 2, because the hydrogen follow the Dewitt rule, so we obtain AX3E1. Now we can find directly the answer, and the answer is AX3E0 for trigonal planar geometry. So this is true for BF3 and GeCl3+. So the correct answer is D.